I think for the last 5 centuries or more, verification and design verification was based on experiments, on tests. Many of you, I guess, are experts in the field, and others might recall this from lab classes. But if you would do a scientific experiment, test or verification with this mouse or rat, how would that be called? Most of you, I guess, would call this in vivo testing. Or if a test would be done on a piece of tissue or on an organ outside the body, that would be ex vivo testing. Or when an experiment would be done in a test tube or on a test plate, in vitro. And what about the Curiosity rover on Mars? How would you call this test on the planet's surface? This would be an in situ experiment, testing in its real habitat. So we have in vivo, ex vivo, in vitro, in situ. How would we classify this then? An aerosol system, or a urine sampling system for first void collection, or this a lab on chip or lab on organ simulation. Well, the scientific expression for computer simulation is in silico testing. In silico, literally Latin for in silicum or in a chip, alluding to the use of silicon for semiconductor computer chips, therefore means performed on a computer or via computer simulation. Reverting back to our design control process. Testing and verification as we all know it today. We are working in a very regulated industry, as it should be. I think that's a good thing. But as testing is time consuming and eating resources, even within the design phase, people tend to be reluctant to change and test too many variants. Indeed, not unleashing all innovation potential. In that regard, simulation or in silico testing is better accessible. You're not testing on a mouse or with a real sample. You're working on a digital twin. A twin that you can copy and paste as many times as you want. So no need for ethics nor approvals. You can't hurt a silicon chip. So all crazy ideas on the table just to check if one might work in a matter of days. I like popular examples. As soon as man started building tools and artifacts, he started dreaming of flying. We have had Icarus, Da Vinci, Michelangelo. They all made their designs of airplanes. But it was not before 117 years ago that 2 bicycle makers from Ohio did the job. The Wright brothers built a plane and flew it down the hills in Kitty Hawk. This too, I think, was in vivo and in situ testing, and I think it's a great page in history. But what history books do not mention is that the Wright brothers had a test team of 9 pilots, and 6 of them crashed deadly testing new designs. And that's a very harsh way of empirical testing. Imagine the claims on that today and the effects it would have on innovation. Today, within silico testing, the only thing that could crash is our hardware system or our software. And we could compare dozens of variants. And in fact, the plane that would be marketed today wouldn't look at this at all, I guess. It would just be the start of a crazy idea. Let me show you some recent examples. I'm not sure if we would have taken the risk to invest in molds for VaxID if we didn't have simulated confirmation of the proof of concept. We were able to test our designs before they were ever built, and I still believe today it's one of the most innovative devices around. With the confidence we gained having simulation models, we built proto-molds that look like this. This, by the way, is candy for designers, and in fact, this was my desktop background, I think, for 2 years. But it enabled us to build proto devices in medical grade polymers, not just using 3D prints, but real injection molded devices. Different device, same philosophy. How to prove that first void urine can be sampled without a medical device in place. How to champion a passive floater concept without budget nor resources for 24 months, for instance. We could bank on simulation technology. After that, we could correlate and further develop the device based on 3D prints, and we've verified a massive amount of 3D printed floaters. Not only for startups, with the same philosophy, we engage with innovation labs of big pharma like GSK. Or in European consortia, for instance, to design a 3D printer for antibacterial polymers. Simulation and digital twinning were key in this project. Within design control, the focus of today's presentation was on that innovation phase and on design verification. And my perception is that it helps companies through the famous valley of death by helping companies optimizing their resources and shortening lead times by digital twinning. I guess most of you know that expression, valley of death. It's the phase where you underestimated the effort to finally industrialize and commercialize your technology. In MedTech and life sciences, however, it doesn't stop there. You might think you're commercial now, but then there's need for more regulatory approval in more regions. Additionally, this is a sector of gold standards. How well will your product be accepted? And hey, of course, you're too expensive and didn't have a reimbursement strategy in place. And why would you, based on all the added value you could offer? And this is what we call the second valley of death. Most startups or companies failing are failing here. So therefore, I thought it could be useful to end with some lessons for successful device or equipment development. I'm using a top 7 format for this, a bit Kai Kawasaki style. Lesson 1. It's a regulated industry. Have a plan in place. Of course, you need added value, but value alone isn't enough. A far cry from it. Design is more than technology and industrial design. Focus on user needs, use flow, the pains you solve, verify and optimize. Create IP. It's a slow and expensive process, and you are too fragile to sweat your way through it without IP. I see this endlessly with companies and projects where planning is half complete, half funded. They hadn't understood all steps that they were going to take. 90% of companies that stall down the road have ran out of time, ran out of money, ran out of something because they didn't know all the things they were going to have to do. Know where you get yourself into. Understand your funding needs, value inflection points, and exit ramps. Very often, big OEMs and large companies would be more than happy to let you do the highly risky part early on. Get off the bus at just the right time. And most importantly, manufacturing and upscaling. It isn't done when you have your final design. This is where the real pain starts. Upscaling, quality issues, get on top of it. I hope this presentation has been useful and that I didn't temper your entrepreneurial spirit too much. So please take the risks, but be prepared. I hope you're all very successful. Thank you.